Hi, Lansing. You ready to do some physics? I am a professor at Michigan State, and I enjoy talking to people who don't do this kind of stuff because it's my opportunity to thank you for the incredible privilege that it is to be able to be supported by the National Science Foundation, which means all of you, and be paid by a great university to teach about these things. And that's pretty amazing. We're all grateful, so thanks very much. So let's do some physics. This is Geneva, Switzerland. It is the former home of John Calvin on the right, Voltaire on the left. It's currently the location of one of the largest scientific laboratories in the world, the European Organization for Nuclear Research, called CERN. They do indeed host the Large Hadron Collider, the LHC, where about 30 of my MSU colleagues and I work, including about 15 graduate students and postdocs, and often 5 or 6 undergraduates. The red circle that you see is this line that runs around the grass and over the roads and the sidewalks and up over the cows. It indicates where the Large Hadron Collider is. It's a circle 27 kilometers in circumference. That's 17 miles for you non-Canadians. Underneath that red circle is where the actual accelerator lives. The accelerator is a string of about 10,000 magnets, many of which are dozens of feet long, many thousands of tons, 120 tons of supercooled helium, because this is a superconducting accelerator, are required. It's the biggest cryogenic engineering facility in the world. Inside of each of those tubes, each of those magnets are 2 tubes evacuated to a vacuum that's close to that of outer space. And in those tubes are counter-rotating beams of protons. 300,000 billion protons. They go around the ring 11,000 times a second, which means that they're traveling at a speed of about 6 miles an hour, less than the speed of light. They're brought to collision in 4 places around the ring, where for the last 15 years we've been building experiments. We work in one of those locations. And then they collide. Now, as you know, our universe was once in a hot, dense state nearly 14 billion years ago. Expansion started. Wait. Yeah, the evidence for the Big Bang is overwhelming. And we're interested in that. Our interest is in understanding the beginning of the universe. We've limited our focus to the universe, modestly. Now, the cosmos did this experiment one time. At the Large Hadron Collider, we do it over and over and over again, 40 million times a second. Now, thousands of people have worked on this for decades. 6 billion Swiss francs have been spent in the creation of this wonderful laboratory. And it's because of that that we're able to do the work that I'm about to describe to you. What I'm going to do is pick out one theme of the many reasons why this device has been constructed and tell you about it. We're confused about mass. Now, some of you probably took a physics course, and for that I apologize. But you probably remember that mass was a central concept. In fact, a defined idea by Newton. Not a property, but a defined idea. In essence, it is a measure of inertia. Inertia is resistance to being accelerated, and so it's easy to push little things and hard to push big things. That's the central idea of mass. But let's make mass weird. To do that, let me give you 2 big ideas. First big idea comes from relativity. In 1905, the young, underemployed Albert Einstein came up with this. Mass is energy, energy is mass, and it neatly fits on a t-shirt. Now, I am a physics professor. I have taken the geek pledge. It means that every time I go out in public, I'm obligated to introduce an equation. You can tell I'm a physics professor because I had ranch dressing for lunch. But for today, because it's TED, You get 2 equations for the price of 1. First equation is E equals mc squared. You've all heard it. You've probably said it. It's easy. In principle, it's an interesting relationship. What it says is that mass has energy. It means that mass is, in essence, trapped energy. And you can find out how much energy there is in mass by multiplying it by a number, in fact, a really big number, the speed of light, times the speed of light squared. Little tiny bit of mass, a lot of energy. Here's the second equation. Frank Wilczek calls this the second law of relativity. Yeah, it's a cheat. There's also a third law of relativity, which I'll leave to you to figure out. It says that if you've got energy, you can interpret that as mass. You can interpret the spring stretched as the spring getting heavier. Okay, so there are the 2 rules of relativity. Here's the second big idea. It's a sophisticated idea of quantum mechanics. And the sophisticated idea is nature's clumpy. Now, in your everyday life, a lot of stuff's clumpy. Stars, Earth, buildings, people. There's no particularly logical reason as to why it is that energy should be granular, clumpy. As you get smaller and smaller below sizes of atoms, energy has particular ways in which it likes to clump. Those particular ways have a name. They're called quanta. We call them particles. And the way to study them is to not chop stuff up. The way to study them is to bang stuff together. So what we do at the Large Hadron Collider and also at the Fermi National Accelerator outside of Chicago is we accelerate beams of protons to very high energies. That makes it possible to produce lots of lots of masses, and the most expensive M's, the biggest masses, can be produced with the most energies in the beam. Now, elementary particles are what results, and you might wonder what elementary means, and it really doesn't mean simple. It means something different. Let's take a carbon atom, 6 protons, 6 neutrons, 6 electrons. That's not elementary because the carbon atom's got parts. It's got moving parts. What about the individual bits of the carbon atom, the electron? Honestly, inside my head on the left side are all the equations and the mechanisms of relativistic quantum field theory. It's really pretty. But on the right side of my head is billiard balls. That's why we call it particle physics. We can't get out of our heads the idea that what we're really talking about are particles, little balls. The electron is elementary because it doesn't have any parts. Nature doesn't allow you to have half an electron. You can have a whole electron or no electrons. How about the proton and the neutron, the pieces of the nucleus of the carbon atom? Nope, got parts. We didn't always understand that that was the case, but we do now. For the last 40 years, we've been studying the inside of the proton and the neutron. We know very well now that they're made up of things called quarks. 2 up quarks and a down quark make a proton, 2 down quarks and an up quark make a neutron. But the quarks themselves, no parts. So quarks appear to be elementary. Okay, so we've got a little list of elementary particles. Electron and its cousins and quarks are elementary. We think. Now let's make it weird. Suppose I took a ton of stuff, chopped it up into 3 pieces, weighed it. You wouldn't have any trouble at all if I told you, and you'd be really surprised if somehow that didn't add up to a ton, right? Let's do the same thing with a proton. Let's take what's inside the proton and weigh it against the mass of the proton. The quark's mass is a tiny fraction of the mass of the proton. The proton weighs much, much more than the mass of the things that make up the proton. We have a reason for that. We understand that now because took a couple of Nobel Prizes to figure this out. In fact, it has to do with what, in fact, holds the quarks together inside the proton. A field called the gluon. We have just a heck of a lot of fun naming stuff in this field. The gluon field is much like the electromagnetic field that's in the room from the lights, from the computers, from WKAR. It's a field. The field of the gluon holds the quarks together. Its sole role is to touch and grab onto quarks. But because it's a field, it has energy. Because it has energy, it provides mass. The inertia of the proton comes not from the things that make up the proton. The inertia from the proton, comes, in fact, from the energy in the field of the gluons. We understand this. It's very predictive, very precise, very pretty, and a complete overthrow of the Newtonian and Lavoisier idea of the conservation of mass. Okay, 2 quarks, up and down. Well, there are 4 more. We've been finding quarks for the last 40 years. The last one, the top quark, was found at Fermilab in the middle 1990s. There could be more. We don't know. That's an object of real interest. Those quarks share a number of properties, but one. They all have different masses. And in fact, the masses are insulting. The mass of the top quark is 170 times the mass of a proton. Ridiculous. No reason why that should be the case. Again, the little up and down quarks have a fraction of the mass of a proton. We need to understand this pattern. We need to understand how elementary particles can have such different masses and, oh, by the way, such absurd masses. So that's the story of what the question is. What's the answer? Well, we have a story about how masses come about. The story's not complete, and that's partly the reason for the Large Hadron Collider. How the electron got its mass, or how the quark got its mass. Same story we think occurred. It's a story about nothing. Really. That is to say, we think the action's in the vacuum in understanding mass. So now we've got to talk about that. Indeed, the observable universe appears to have started from a tiny ball of space and time and energy 13.7 billion years ago. And then it started to expand. But as it started to expand, it cooled off from its original incredibly hot temperatures. Temperatures so hot that it would be impossible for anything that had parts to stick. So only elementary particles could possibly exist in the early universe. Now you begin to get the idea of why we're interested in the beginning of the universe, because we make those conditions over and over and over again that have only elementary particles. Okay, the universe is very hot. Inside the universe, we think, were all the elementary particles that we know and love, and those that we haven't yet found, all zipping around at the speed of light because they haven't got any mass. The universe expands, and then a magic temperature appears to be reached. Much like water freezes, the entire universe underwent a phase transition. Everything, the entire universe. And at that point, all those particles that were zipping around at speed of light suddenly slowed, immediately slowed, because they immediately got a mass at that temperature, and they've had those masses ever since. Wow. What we think happened was, while it was hot, the vacuum was the vacuum, empty. At that temperature, the vacuum got full. Full of what? I know you're asking yourself. We'll take out a piece of paper, a number from 1 to 10. We'll have a quiz afterwards. We think it's full of something called the Higgs Field. Peter Higgs is a Scottish physicist who's now retired and had the clearest enunciation of this idea among a number of people that had the idea about the same time. This often happens in science, by the way. The Higgs field, well, it's a field that has energy. Since nature is clumpy, there has to be a particle associated with the Higgs field. It's called the Higgs particle. The Higgs boson is what we actually call it. To be really geeky, you can use that. The Higgs boson. The Higgs boson populates the vacuum. The vacuum is full of Higgs bosons. And the Higgs boson has a job. While these particles are still flitting around, remembering that time that they were massless, they don't go very far now because they are in the vacuum, or they see the vacuum, and what's there is the Higgs boson, and its job is to grab onto these elementary particles. Once it grabs onto them, it gives them mass. So each one of the elementary particles that we know gets its mass, we believe, through its interaction with the Higgs boson. Now, the fact that each one is different, that's a major question. We'd like to understand that. Here's a Higgs boson metaphor. David Miller invented this a number of years ago. It's just really very nice. The metaphor goes like this. You've got a room with lots of people talking in it. The energy level's high. They're all random. There's no particular direction singled out. And then there's, by the way, that room then, those people are the Higgs Field. And they hear a laughter on the outside, a really loud laughter. The room goes silent. Everybody looks in that direction. But for you geeks, the symmetry was broken and the lower symmetry results. And everybody picks out a special direction in space because Quark Carl Good has arrived. Now, Quark Carl Good is off of his crutches now, and so he's flitting about the outside of the room as only Carl can flit. He's flitting about the entire outside of the room at the speed of light because he doesn't have any mass. He goes into the room, and because everybody likes Carl, everybody wants to get near him. All of a sudden, he's having trouble. He can't flit anymore. It's as if he's gone into a viscous medium. And that viscous medium acts as if he has gained inertia. What's inertia? It's the resistance to acceleration. What's that? That's mass. By virtue of the fact that Quark Carl Good entered the Higgs field, he got inertia, he got a mass. That's how we think the Higgs boson works. So mass is a very funny thing. Mass was born. There was a time in the history of the universe where there was no such thing as mass. Then that magic temperature occurred. The Higgs boson arrived, built out of the vacuum, and that's a really interesting story, but we're not going to go into that. The Higgs boson arrives, and then things have mass. Mass is an emergent quality. It's an emergent feature of cosmology, a linking of particle physics with cosmology. So the 6 quarks. Because the electron has 5 cousins. The particles on the bottom are the messenger particles of the fields. These are all what we know about. They explain an awful lot about our world, but we have to find the Higgs boson. The Large Hadron Collider was built with parameters that are specifically designed in order to be able to find the Higgs boson. Okay, here's another story about mass. This one's an embarrassment. Anybody know what this is? It's the Andromeda galaxy. It's our nearest spiral neighbor, 2.5 million light years away. It has about 1 trillion stars. That's what holds it together, because the stars are big, right? Stars are massive. The gravity of those stars, helped by the presence of a big black hole in the center of the galaxy, hold that thing together. Well, like all galaxies, it remembers the original rotation of the particles that made it and the stars that made it, and so it's rotating today. And astronomers can very carefully measure the speeds of the rotation. Now, there's no way in the world, it turns out, that the outer edges of that galaxy can be moving at the speeds that they are and still be bound to the galaxy. There is not enough mass in the stars to be able to hold those outer edges in place. There's something else, because all we know about are the masses associated with the stuff that shines the stars. We add that up. But there's something else that's not shining that is providing gravity. We call it dark matter. And astronomers can calculate how much dark matter is required in order to give Andromeda the speeds that it's got. And it turns out to be a halo, a big halo surrounding the galaxy, surrounding our galaxy, surrounding many other galaxies, indeed surrounding clusters of galaxies, because they too would not hold together. Well, you know the story by now, right? If it has a mass, it's got an energy. If it's got an energy, nature's clumpy. So there has to be a particle associated with dark matter. The dark matter particle, another object of discovery for the Large Hadron Collider. So the challenge is understanding mass. How do we do that? We do that with ATLAS. ATLAS is 2 things. ATLAS is a bunch of people. It's 1,900 people from 165 institutions in 35 countries around the world. We like to say that the sun never sets on the ATLAS collaboration. But ATLAS is also a very large detector. It's a device that we've been building for 15 years. Many of the components in that thing were built in our laboratory down the road, as well as in the older building that we used to establish. ATLAS is 80 feet high, 150 feet long, 7,000 tons, 3,000 kilometers of cable, 100 million electronic channels. It's working. It's so large that if you dropped it on the pitcher's mound in Wrigley Field, it would dominate the entire infield. because something, by God, has got to dominate the entire infield from the pitcher's mound at Wrigley Field, especially in middle innings. So proton beams come in from the side, they collide exactly in the center of the detector, and then thousands of particles are produced. We detect them, we characterize them, we send them off for analysis, including to Michigan State at Michigan, where we have a special computer system to do this. This is Fabiola Gianotti. She is a Milano physicist and our boss. She's the scientific spokesperson for the Atlas collaboration. This is just about 1 p.m. on the 30th of March. We're all awaiting the first collisions at the Large Hadron Collider just a few weeks ago. And indeed, at 12:58, it happened. There are 4 languages in that room that could be spoken, but everybody said, wow. Some variant of wow works in all those languages. And of course, Fabiola looked a whole lot happier after that occurred. Here's a cartoon of that first event. Protons coming from Switzerland, protons coming from France, colliding right in the center of the detector and making the very first collision. And then a computer reconstruction of all the tracks and everything that happened. Now, we've been running ever since. We're going to be running for the next 20 years. This is the wonderful Hubble Space Telescope, and a picture that the Hubble Space Telescope took in 2003. It's called the Ultra Deep Hubble Field. For many, many days, they watched a particular spot in the sky near the constellation Orion, in a spot that's not much bigger than the tip of your finger, a meter away from your head. What they found was a layer of our ancestry. The nearest stars easily visualized. The more and more they looked, the fainter and fainter they saw galaxies. The faintest objects on here are from the original nursery of galaxies, not more than about 700 or 800 million years after the Big Bang. 13 billion years that light traveled to get into the eye of the Hubble. This is just about as far back as we can see. Now, there could be neutrinos from the Big Bang. We're certainly bathed in an ocean of microwaves left over from 300,000 years after the Big Bang. Your TV set can pick up that microwave signal. You'll see it as part of the static before the digital conversion. But seeing further back is we're just about done. In order for us to understand what happened before about the first minute in the beginning of the universe, we've got to do like Jurassic Park. We can't look at relics of dinosaurs. We've got to go make our own dinosaurs. That's what the Large Hadron Collider does. We recreate those conditions in the Atlas detector. Those of you that have toddlers, by the time they go to college, they're going to study more about the origins of us, the origins of the universe, than we know now. And it's really exciting to me that some of those origins come from the work that we're going to do. Einstein famously said that the most incomprehensible thing about the universe is that it's comprehensible. And as I get older, it becomes more and more apparent to me that that's the case. Thanks very much.